3.5 Knowledge of Statistics. A proper knowledge of statistics is vital in all forms of research. To understand anything about the world, you must understand it at a quantitative level. This is something anyone can do. Anyone can make a table and distill much of the complexity of the world into a few indicative statistics. In order to understand, for example, how wealthy Ireland is, you cannot just travel to Ireland and jot down your impressions. Which part of Ireland did you see? How many houses did you see? Did you have the ability to evaluate the value of goods, houses, industrial equipment, cars, clothes, just from looking at them? It is impossible to understand the world from a purely experiential level, and so you must use statistics. Of course, it is possible to lie with statistics, but it is much easier to lie with anecdotes. A statistic almost always has some source, government agency, a study, and while those can be fabricated, it is more difficult to do. Moreover, there are statistical plausibility tests which can be used on all manner of data, which would draw red flags to statistics. While these tests may not catch fraud 100% of the time, they serve as an additional barrier to lying about the raw data itself. However, most of the time, raw data isn't outright fabricated. The way people lie with statistics is either cherry-picking and hoping the viewer doesn't know about the cherries not picked, or come up with some inclusion criteria that excludes data which would otherwise be relevant to the point you're making. It's all terribly complicated, and there's no simple way to determine if a statistical argument is correct or incorrect, or honest or dishonest. You just have to know things. Unfortunately, even if they don't say so, the general public usually outsources the answer to these problems with academic consensus. And there are several problems with this as stated before. However, in this section we will just be dealing with the question of general statistical competence of academics. Are they much better than that of highly motivated amateurs? Well, perhaps, as a rule, professional researchers have had more statistical training, and this fact alone, in the absence of any other information, would make it prudent to assume that they are generally better at interpreting statistics. But we have more information. We have several studies which tested the statistical knowledge of academics, and what they found was that, in terms of dealing with the kinds of problems one faces when doing real-world experiments, academics come off rather poorly, getting the equivalent of D and F grades on most of these tests, and not significantly better than first-year college students, which is relevant to the viewer who likely has the same level of education as a first-year college student. So, let's get into it. 3.5.1 McShane 2016. The paper Blinding Us to the Obvious, the Effect of Statistical Training on the Evaluation of Evidence by McShane and Gall gave several simple statistical questions to multiple types of academics to see how well they could answer them. One of the questions, presented below, was presented to 75 researchers who had published in the New England Journal of Medicine. The question was as follows. Below is a summary of a study from an academic paper. The study aimed to test how different interventions might affect terminal cancer patients' survival. Participants were randomly assigned to one of two groups. Group A was instructed to write daily about positive things they were blessed with, while Group B was instructed to write daily about misfortunes that others had to endure. Participants were then tracked until all had died. Participants in Group A lived on average 8.2 months post-diagnosis, whereas participants in Group B lived on average 7.5 months post-diagnosis. Which statement is the most accurate summary of the results? Very verbose. Here's a layman's phrasing of the question. Which group lived longer? Group A? Group B? They lived the same? Or it cannot be determined? This is not a trick question. It is, in fact, as simple as it seems. Which group lived longer? Yes, the correct answer is Group A. Here were the results from the authors who had published in the New England Journal of Medicine by p-value assigned to the results. When the authors were presented the data with a p-value of 0.01, they answered A, the correct answer, 95% of the time, 83% of the time, and 88% of the time. Pretty good. Perhaps not as high as you'd hope, but pretty good. When the p-value was 0.27, they answered A, only 10%, 22%, and 3% of the time. What this shows is that the authors of articles published in the New England Journal of Medicine overwhelmingly failed to distinguish statistical significance from descriptive statistics. A p-value of 0.27 is not a statistically significant result, but these authors then went on to say what happened didn't actually happen because it wasn't statistically significant. Say your vertical leap is 4 feet, and Bob's vertical leap is 3 feet. Whose vertical leap is higher? Yours. Oh, but n equals 2. That's statistically insignificant. We cannot say you can actually jump higher than Bob given such a small sample. That's what they're doing here. As a layman, this appears incomprehensibly stupid. However, there is a phenomenon among military aircraft pilots called CFIT, or Controlled Flight into Terrain. It is when a pilot is so focused on his instruments and making sure the aircraft is running properly that he loses track of where the aircraft is headed relative to the Earth. Something you could see by just looking out of the window. It's not that the pilot is incomprehensibly stupid, it's that he is so fixated on his instruments that he ends up losing track of the big simple. And that's what's happened here. Academics so fixated on their statistical instruments that they lose track of the big simple. Similar questions were given within the paper. The second question was given to 299 researchers who had published in the American Journal of Epidemiology. Below is a summary of a study from an academic paper. The study aimed to test how 2 different drugs impact whether a patient recovers from a certain disease. Subjects were randomly drawn from a fixed population and then randomly assigned to drug A or drug B. 52% of subjects who took drug A recovered from the disease, while 44% of subjects who took drug B recovered from the disease. A test of the null hypothesis that there is no difference between drug A and drug B in terms of probability of recovery from the disease yields a p-value of 0.175. Assuming no prior studies have been conducted with these drugs, which of the following statements is most accurate? The answers the researchers could choose from can be paraphrased as A. A random person taking drug A would be more likely to recover than someone taking drug B. B. A random person taking drug A would be less likely to recover than someone taking drug B. C. A random person taking drug A would be equally likely to recover than someone taking drug B. D. It cannot be determined. Again, this is not a trick question. Even a statistically insignificant result does not mean the effect isn't real, just that the probability of the results being caused by something other than the difference in treatment, or just random noise, is higher. Like with the first question, the authors were asked to answer the same question, but with the p-value manipulated. The result was that only at p equals 0.025, statistically significant, did the respondents correctly choose answer A, a majority of the time in both groups. The treatment difference size was also manipulated, with the small effect being 52% versus 44% recovery, and the large effect being 57% versus 39% recovery. And when the effect was larger, the researchers were somewhat more likely to choose A in all conditions, as you can see. Interestingly, in terms of choice, when the authors said what drug they would choose for themselves, they were much better at choosing A. But even in the large treatment difference group, it was only around 50-50 for the not statistically significant results. McShane and Gall's work is interesting because it's an example of academics being wrong in a way that laymen would not be, and this effect is systematic and is apparently caused by their statistical training. 3.5.2 McShane 2017. In 2017, McShane and Gall asked the same questions we presented to you at the beginning, looking at cancer life expectancies for those who were told to write about their blessings or write about the misfortunes of others. This was asked of 117 authors of articles published in the Journal of American Statistical Association. McShane and Gall contrasted the results from the Journal of the American Statistical Association, JASA, with the results from the New England Journal of Medicine, NEJM, and found that when the results were not statistically significant, the JASA respondents were more likely to correctly answer A. McShane and Gall then repeated the second question from 2016 about the effectiveness of a drug, and compared the results from JASA to the American Journal of Epidemiology, AJE. In terms of the proportion choosing option A, drug A is more likely to have a beneficial effect, the proportion of the JASA respondents who correctly chose answer A was only 63%, even when the p-value was 0.025, a worse performance than the AJE respondents. At lower p-values, the JASA responses were even more dismal, 22%, 21%, and 6% respectively. What these studies show is that epidemiologists and statisticians don't really know what p-values and statistical significance mean in a practical sense, and that there is no important difference between statisticians and epidemiologists on this matter. 3.5.3 TLAU 2019. In a 2019 paper, Beyond Psychology, Prevalence of P-Value and Confidence Interval Misinterpretation Across Different Fields, the authors TLAU, Zhu, Zhao, Zhou, and Hu gave a series of false statements about p-values and confidence intervals to 1,231 mainland Chinese academics, and 248 academics who are Chinese nationals abroad. These were the results as reported by TLAU et al. We then converted these into average number of errors made by each field for the p-significant, ci-significant, p-insignificant, and ci-insignificant questions. The total number of endorsements of incorrect statements are out of 16 maximum. Within each question category there are 4 false statements. Psychology scored very near the average, scoring 8.51 versus 8.56 for the whole field, beat out only by the results from math and statistics, which scored 7.05 out of 16. The similar performance of psychology in comparison to other fields is important, because it makes it implausible that the problems academics have in interpreting statistics is limited to psychology. In fact, by focusing on psychology, you end up missing the fact that psychology is almost precisely typical in having these kinds of problems. TLAU also showed the total percentage of respondents who endorsed at least one false statement by whether they were Chinese nationals abroad or if they were Chinese on the Chinese mainland. The Chinese on the Chinese mainland may be marginally worse than Chinese abroad, but it's also possible that non-Chinese academics in the West are worse at interpreting statistics than Chinese in China. But there's no good reason to reject data on Chinese academics as not being applicable to the West, unless there is some very compelling reason to do so. 3.5.4 Zuckerman 1993. In 1993, in the paper Contemporary Issues in the Analysis of Data, a survey of 551 psychologists, Zuckerman et al. Looked at the scores of 508 psychologists, broken down by being full professor, associate professor, assistant professor or student, on 5 first-year statistics questions. These questions were all true or false, so random guessing would give a score of 0.5. 3.5.5 Hoekstra 2014. The paper Robust Misinterpretation of Confidence Intervals took 594 first-year psychology students, master students, and researchers from the University of Amsterdam and gave them 6 statements about confidence intervals. All 6 of these statements were false. They then asked the respondents to either endorse or reject these statements. The average number of false statements endorsed by education levels were 3.43 for researchers, 3.23 for master students, and 3.52 for first-year students. In this sample at least, the population that endorsed the fewest false statements were master students, then researchers, then first-year students. On the predictions of effort made by behavioral economists, PhD students performed better than PhDs.